This is problem 153 from chapter 12. The motion of a particle is defined by the equations x is equal to 2t plus t squared and y is equal to t squared. Both are in meters when t is in seconds. We want to determine the normal and tangential components of the particle's velocity and acceleration when t is equal to 2 seconds. So they're giving me a function for x and y, from which, by taking time derivatives, I can find the velocity and the acceleration in rectangular components. If I have the velocity vector in rectangular components, I should be able to figure out that same velocity but in normal and tangential components, and same thing with the acceleration. So let's see what we have. So the first thing that I'm going to do is just figure out what the velocity vector is in rectangular components. So to do that, I need to take a time derivative of both x and y. So x dot is equal to, taking the time derivative here, just gives me 2 plus 2t. And then for y dot, I have t squared, so taking one derivative would be 2t, and that was so much fun. Let's just do x double dot and y double dot straight off. Okay, so taking the time derivative of x dot just gives me 2, and taking the time derivative of y dot gives me 2. So now I can write the velocity vector and the acceleration vector, but in rectangular components. So the velocity, using my equation here, is 2 plus 2t I hat plus 2t j hat, and the acceleration is v dot, x double dot is 2, so that's 2 I hat plus 2 j hat. So the acceleration does not depend on time, so it's constant acceleration. The velocity does, and we're looking for the components when time is equal to 2 seconds. So let's go ahead and say what the velocity is equal to when t is equal to 2 seconds. So that would be 2 plus 2 times 2. 2 times 2 is 4. 4 plus 2 is 6. So this is 6 I hat plus 2 times 2 is 4. So that's 4 j hat. Okay, now for finding the normal and tangential components of the velocity, well, this is actually pretty easy because there is no normal component, or the normal component is 0. So the magnitude of the velocity is the tangential component. So let's find the magnitude of the velocity by squaring the components, the x and y components, adding them together, taking the square root, and you can do that on your calculator. You should get 7.211 meters per second. I'm going to write this out using my equation here. So the velocity vector now in normal and tangential components is 7.211 meters per second in the tangential direction. Okay, and then finally we'll say, to give the normal and tangential components, this is the tangential component, so the tangential component is 7.211 meters per second, and the normal component always, for the velocity, is 0, because the tangential direction is defined by the direction that the object is going in, so there can never be a normal component for the velocity. Okay, so now I have to turn my attention to the acceleration. I'm going to show you two different ways for finding the normal and tangential components for the acceleration. The first way, which I think is what they would do in the book, is to draw a figure, and we're going to put the velocity vector on our figure. This, first of all, we're going to use rectangular components, and my velocity at 2 seconds has an x component of 6 and a y component of 4. So over 6 and up 4. I'm not going to be too concerned with getting the direction exact, but the velocity vector is going to look something like this. I'm also going to be kind of tight on space here, But there's our velocity vector, and the angle here is theta, and I said I was going over 6 and up 4. Yeah, I'm not going to, I don't know. I can try and put that on the figure. I might regret this later when I run out of room, but there we go. Okay, so that's for the velocity, and so I can find the angle theta by doing the inverse tangent of the y component divided by the x component, so the inverse tangent of 4 over 6, that gives me 33.69 degrees. Now, I want to go from rectangular to normal and tangential, and we know the velocity is pointing in the tangential direction. So this angle is the angle between the x-axis and the tangential direction. And perpendicular, I didn't draw that quite right, it should be right on the line there. Perpendicular to the tangential direction is the normal direction. Okay, so now I can use my acceleration vector in rectangular components, and the acceleration is constant, and it's 2 in the x direction and 2 in the y direction. We don't really even need to use a formula to figure out the angle there. If you're going 2 over and 2 up, that angle must be 45 degrees. So there's my acceleration vector. Has different units than the velocity vector, so the two lengths don't really tell you anything there. And this angle here, which we're going to call phi, is 45 degrees. So then this angle here is 45 degrees minus 33.69 degrees, which is 11.31 degrees. Now, I hope you see where this is going. We have our vector here. We want to break it down into components. This is kind of like back in Physics 161 when we were looking at forces on something that was on an incline, and we used a tilted coordinate system. So our coordinate system that we want to use here is the normal and tangential coordinate system. Remember, this angle is supposed to be 90 degrees, even though it might not look like it. And I know what this angle is. So then I can just use sines and cosines to find the normal and tangential component for my acceleration vector here. So the tangential component, that's going to be the cosine component when I use this angle here. So if I take this vector and break it up, let me redraw this. So here's the tangential direction. Here's the normal direction. Here's my acceleration vector. And this angle here is 11.31 degrees. I want to break this vector down into components. A tangential component here and a normal component here. If I take the magnitude of the acceleration, which I didn't find, so now I need to find that. So the magnitude of the acceleration is the square root of 2 squared plus 2 squared, and that is 2.828. Okay, so that's the magnitude of my acceleration vector there. So I have 2.828 times for the tangential component, that's going to be cosine of 11.31 degrees, and that is 2.773 meters per second squared. There's the tangential component. The normal component, 2.828 for the hypotenuse, and then sine of 11.31 degrees, and that gives me 0.555 meters per second squared. Okay, so I found everything that I needed to find, and you should know how to solve the problem this way by drawing the diagram, because that's going to appear again later on in this course. But there's another way we could have solved this. So let's look at that just for fun. So I know the magnitude of the acceleration, and to do this, let me just write out what this formula was. This is the x component of the acceleration squared plus the y component of the acceleration squared, and that gives me the magnitude of the acceleration. But you can see from our diagram here, if you have the normal and tangential components, you could also use that to find the magnitude of the acceleration. We did it the other way around, but you can say the tangential component squared plus the normal component squared gives you the magnitude of the acceleration. So this must be equal to 2.828. Then we can square both sides of the equation, and we can say at squared plus the normal component of the acceleration squared is equal to 2.828. Now, if I knew either the tangential component of the acceleration or the normal component of the acceleration, then I could use this equation to find the other component of acceleration. And if I go back, to my equation that I have here, the tangential component of the acceleration is v dot, which I can find. The normal component is v squared over rho. I have v at 2 seconds here. If I knew what rho was, then I could find, that would the normal component of the acceleration, and then I could use this to find the tangential component of the acceleration. I'm not going to do it that way, but you have an equation here which you could use to find rho. Instead, I'm going to find v dot, and then you can use this equation to find the normal component of the acceleration. So for v dot, we have to be careful here because remember v is the speed, not the velocity. So if I want to use this expression here to find the speed, that would be the magnitude of the velocity. But I can't write it at 2 seconds because I have to find the magnitude of the velocity first and then take the time derivative. So if I do this, but not for the velocity at 2 seconds, but just for the velocity at any time, then I have, okay, we're going to have to take the time derivative of this, but the magnitude of the velocity at any time t would be 2 plus 2t squared plus 2t squared. And then if you take, because we're looking at 2 seconds, if you take that and plug it into what I have in parentheses here, you should get back the 6 squared plus 4 squared. Okay, so in parentheses here is the magnitude of the velocity as a function of time. Then I take the derivative with respect to time, and I'm not going to do all the work for this, but when t is equal to 2 seconds, you should have v dot is equal to 2.774 meters per second squared. This is how the speed is changing. This is the tangential component of the acceleration. You could take that, put it in here, and then solve for the normal component of the acceleration. So that's another way that you could do that. And that concludes problem 153.